All right, so we started 3.1 last time, and we got to the point where we had talked about the different models for subtraction. That's where we left off. Does that sound about right to you guys? And just as a reminder, there were, I think, 4 models. One of them is the takeaway model. The second one was the missing add-ins model. The third one was the comparison model. And then the fourth one was the number line or measurement model. Okay? So we are at the point where we have got example number 4. Create a word problem for each of the 4 models for subtraction. So that's what you guys are going to do next. So within your group, I want you to create 4 different word problems. And they should all be different because as we talked about when we did these different models, there are different connotations to what's really going on when you're doing comparison versus takeaway. Okay? So in your group, I want you to create 4 different, questions that you could ask a second, third grader or whatever that would demonstrate these different models for subtraction. Okay, so that's what you're going to be doing for the next few minutes. Okay, so what we're going to do next, so that you've had a chance to create these problems, is that I'm going to have each of you give an example of each one. Okay, so there's 5 groups in here, which doesn't work out very nicely with 4 problems. So what I want to do at least is to have 2 examples of each problem. So take a look at the ones that you've got and decide maybe which one you really like the best or want to share. You need to pick 2 of them, okay? So pick 2 of them. I don't really care necessarily which ones, except to say that I need to have at least 1 example of each of the 4 as we go. Take a look and see which ones you liked on your problems that you created. I'll just decide to do that. Okay. So what I'm going to do then is I want to have a group give me an example of a takeaway model. So what is a takeaway model that you did? We're not going to write it down. We're just going to verbally say it. Yes.
Okay. We said if Jane has 12 cupcakes and Jack eats 3 of them, how many cupcakes does Jane have left?
So Jane has 12. Jack eats 3. He has taken some away. Very good. Does anybody else want to share a takeaway model?
Jimmy had 8 cookies. Phoebe ate 3. How many does Jimmy have?
All right. So we're enjoying eating.
Yeah.
He's hungry right now. It's going to make me hungry. All right. And I've already had lunch, so that's not good. Anybody else want to share a takeaway? Okay. How about missing add-in? What do you have?
Let's use it like 20 bucks from
All right. So she's collecting bugs, and she has found so many that she needs for a project, but not all of them yet. So she's missing some. Right. Okay. What's another one you got?
Farmer Joe needs 12 feet of fencing. Mary has 8 feet. How many more feet of fencing does he need?
Okay. And your feet of fencing one actually could be used for that. It's a missing one. What else could it be used for? It could be used for that number line measurement model because it's a feet problem where you can actually subdivide it and it makes sense. So either one actually work on that one. Anybody else want to do a missing add-ins model? Do you want to do one? Do one for me.
Said Joey and Chandler need 5 apples to make an apple pie. They had picked 2 apples off the tree. How many more do they need? That'll work.
Okay. Let's do the next one then.
Awesome.
Comparison. What do you have? Comparison model.
Bob and Larry are playing soccer. Bob scores 4 goals and Larry scores 1 goal. How many more goals does Bob score?
So we've got sports going on with this one, yeah? Good. All right, what else? Comparison.
We have one.
Okay.
If Molly has 10 Barbies and Sally has 4 Barbies, how many more Barbies does Molly have than Sally?
Awesome. So we've got a girl problem to balance out the boy problem with soccer, right? Okay. Good. I only called it a boy problem because you gave boy names, because I do realize of course that you ladies can play soccer too. Any others you have for comparison? Okay. How about number line measurement? All right, Marilee, I want you guys to share yours because you made me laugh.
Lucy joins the same performance with the goal of losing 10 pounds. So far, Lucy has lost 6 pounds. How many more pounds will she lose to reach her goal?
Excellent. Got pounds in there. So it isn't just distances like you guys were asking, right? What else? Yeah, Katie?
Sure. We're doing number line right
Uh-huh.
Hunter rides back to school, which is 10 miles away.
Whoa, man, that's far away from your rod. That'll work. That's
Her
okay.
numbers.
Very good.
He
All right.
stops at a donut shop, which is 5 miles away from the school. How far from home is he?
Well, he's gonna ride off the donuts.
Awesome. That's right. He might as well stop for doing so he's right 10 miles. All right, so this is the kind of thing that you should be thinking when you're working with children in takeaway or children with subtraction. Because if they struggle with an idea and you can identify, oh, every problem that they get wrong is a comparison model, then you know the problem. You know what it is that they're actually struggling with. It's not the subtraction, it's understanding that this model is going to create a subtraction problem. So that's why we're looking at this, okay? There's one more slide for us to do in this lesson. And this is a slide about properties. Okay, so we talked about addition properties. So without looking at your notes, everybody eyes on me. Remember, or somebody tell me what you remember. What is an addition property that you remember we talked about on Wednesday?
A plus B equals B plus A.
Okay, and do you remember what that one was called?
Commutative.
That's commutative. So commutative was one of my properties. Associative was another one, and that had to do with what was grouped inside of parentheses. We had a couple more. Identity, and what is the identity element for addition? Zero. Thank you. Yes, it is zero. Yeah, it's okay. And then there's one more property that was the weird one. No, we haven't got to distributive yet because we haven't gotten to multiplication yet. It's called closure. Remember we closed the door, at least in our minds, and we said we had numbers floating around in the room. We took a couple numbers and we combined them with addition and created another whole number. What about whole numbers being closed? Okay, so this slide we're going to talk about subtraction with that issue. The question is, which of the following properties hold for subtraction? All right, so closure is the first one asked about. Closure, again, is the idea that if I take two numbers and I combine them with this operation, and my operation right now is subtraction, do I always get another whole number? No. So Marilee says no. Can you give me an example? Why not?
3 minus 5 is negative 2. The negative's
So we took two whole numbers and we subtracted them, and when we subtracted them, we did not get a whole number. So there is no closure property for subtraction with whole numbers. Now, if we broaden our universe, which we will in chapter 5, to include negatives, then we would be okay. And we will do that then, but not with whole numbers. Next one, commutative. So Morgan told us commutative is this idea of switching the order of things. Can I do that with subtraction? Lynn says no. Give me an example, Lynn.
5 minus 3.
So 5 minus 3 is 2, 3 minus 5 is negative 2. I don't get the same thing, right? This worked for addition though, right? It really did. It was just fine with addition, but it doesn't work with subtraction. So, yeah, no commutative property for subtraction. And I actually don't even get that when I introduce integers, do I? I mean, I get a negative integer, but it's still not the same integer. So this one fails, subtraction fails for all of our number systems that we work with anyway. What is associative? So 5 minus 3 in parentheses, and then what percent?
Minus 2.
Okay.
And then, oh well, are you bigger?
It's okay, we can go with this. It'll still be alright.
Equals 5 minus, and then 3 minus 2.
Okay, so let's use these numbers and see what happens. See if we end up getting the same thing. Alright, so what is 5 minus 3 in the parentheses? 2. And then 2 minus 2 is 0. Alright, so over here, what is the 3 minus the 2? And 5 minus 1? And they are not the same. So, no associative property either, right? And by and large, I mean, there are examples you could use of specific numbers that would make this work, but nearly any one you probably would try to use is not going to. So it's nothing special about the 5 and 3 and 2. Last one, identity property. What do you think? Okay, so Lynn, you're saying yes. Why? That is a true statement. So let me give an any number. Okay, so that's true. It would work. Do you remember what the identity property had?
Remove the 0 and do 0 minus 7.
Yeah. The identity property has to work in either direction, and then we run into a problem. Because if I do it in the reverse order, it doesn't end up working. So it's sort of like we have half of an identity property, right? But since I don't have the whole thing, I don't actually have an identity property either. And of course, that's sort of interplaying with the idea that I don't have a commutative property, right? So the order doesn't matter on subtraction. So we fail to get any of our properties with whole number subtraction that we had with whole number addition. All right, so jot these down if you don't have them, the homework for these. And then I'm going to open up, well, I'm going to open up some of the